On November 9th, 2025, astrophotographer Frank Nebling captured an image that sent shockwaves through the astronomical community, a rare display of twin ejections with one stream astonishingly aimed toward the Sun itself. The photograph reveals a complex structure of light and motion, suggesting hidden processes beneath the comet's icy surface. For researchers, this isn't just a striking image, it's evidence that challenges what we thought we understood about interstellar visitors. What Nebling's lens captured was not a simple cometary tail blown outward by the solar wind, but a structure of exceptional complexity. A bright fan-shaped anti-tail extending millions of kilometers into the dark, and another narrow stream of matter thinner and sharply defined pointing straight toward the Sun. This geometry immediately sparked debate among researchers. By all classical understanding, cometary tails are driven away from the Sun by the relentless pressure of light and charged particles. To witness a counterflow, a jet of material moving in the opposite direction, is like seeing the wind blowing both ways at once. And yet, that is precisely what the image seems to display. At nearly the same moment, this image appeared online. Harvard astrophysicist Avi Loeb published a new analysis of the anti-tail and sunward ejection of 3I Atlas. In it, he examines the peculiar morphology of the streams and asks a question that bridges science and imagination. Could such ejections be entirely natural? Or might we be observing a behavior that hints at something more? The paper is careful, methodical, and deeply empirical. Loeb insists that speculation must always follow evidence, not precede it. Still, the data raise questions that do not fit easily into familiar models. Atlas acceleration, its changing luminosity, and now this astonishing tail configuration form a puzzle unlike any other we've encountered from the depths of interstellar space. To understand why this is so unusual, let's recall that 3I Atlas is only the third confirmed object from beyond our solar system. Before it came Oumuamua in 2017, an enigmatic traveler that accelerated without a visible tail, and 2I Borisov in 2019, a more conventional comet whose behavior aligned with expectations. Atlas, in contrast, seems to stand at a crossroads between these two. It displays the activity of a comet, yet the dynamical oddities of something that refuses to obey the gravitational script written for it. Since its detection earlier this year, it has surprised observers at every stage of its journey: bursts of brightness, measurable shifts in trajectory, and now a phenomenon that defies the geometry of sunlight itself. The anti-tail visible in Nebling's image could in theory be explained by a simple alignment effect. When Earth crosses a comet's orbital plane, debris scattered along that plane can appear to point toward the Sun, creating the illusion of an inverted tail. This phenomenon has been seen before, rarely but enough to be understood. Yet, what makes Atlas so confounding is that its anti-tail isn't alone. Alongside it lies a direct ejection, bright and compact, unmistakably flowing sunward. This is not an optical trick of perspective. Spectroscopic analysis of the image confirms the presence of distinct materials moving in different directions, forming a genuine dual structure. The comet, it seems, is not merely reflecting sunlight. It is actively sculpting its own pattern in space. For Avi Loeb and his colleagues at the Galileo project, this observation has profound implications. If these ejections arise from natural causes, they might reveal new kinds of sublimation processes acting on interstellar ices compounds that evolved in environments far colder, darker, and older than our own solar system. But if the ejection's motion duration or stability cannot be explained by sunlight and rotation alone, then scientists will need to consider more unconventional interpretations. Loeb stops short of claiming anything extraordinary, but he does not dismiss the possibility that interstellar objects might one day show evidence of artificial design. Science, he reminds us, must always follow where the data lead. The data in this case are fascinating. Analysis of the anti-tail indicates that it's composed mainly of microscopic dust grains, tiny remnants that scatter sunlight into a soft golden glow. The sunward ejection, however, is of a completely different nature. It appears gaseous, made mostly of carbon monoxide and ammonia with only trace amounts of water vapor. This is an unusual signature. Most comets from our solar system contain abundant water ice that dominates their emission spectrum when heated. Atlas' relative dryness could suggest that it formed in an environment depleted of oxygen-bearing molecules, perhaps the outer regions of another star's disk. It's a time capsule from another sun carrying chemistry we've never directly encountered before. As December approaches 3I, Atlas will draw closer to Earth, providing astronomers a rare opportunity to study an active interstellar comet in unprecedented detail. Observatories across the globe are preparing coordinated campaigns. The European Southern Observatory's Very Large Telescope will measure the composition and velocity of the outflows. NASA's Hubble Space Telescope is scheduled to obtain ultraviolet and visible light images, while the James Webb Space Telescope may target the object's infrared spectrum to identify organic molecules. Even the Juno spacecraft orbiting Jupiter will turn its radio antenna toward Atlas next March, searching for any signals or emissions similar to those briefly detected in October. Faint whispers from the cold nucleus of an interstellar traveller. The earlier radio detections captured by South Africa's Meerkat array already hinted at the presence of hydroxyl radicals, a byproduct of water sublimation. That suggested Atlas was venting vapor as it warmed near the sun. But the persistence and direction of the new ejection challenge that simple explanation. Normally, solar wind pressure would quickly disperse any material emitted sunward. Yet in the new photographs, the sunward jet remains sharp, coherent, and brilliantly luminous. It behaves almost as if sustained by an inner force rather than external radiation. Some researchers propose that Atlas' nucleus may be rotating unusually slowly, allowing certain regions to maintain near-constant solar exposure and produce a stable jet. Others suspect compositional layering pockets of carbon monoxide ice, trapped beneath denser crusts that erupt explosively when sunlight finally penetrates. Each theory has merit, but none fits all observations perfectly. Adding further intrigue, astronomers have identified another object, C2025V1, moving between Earth and 3I Atlas. Loeb clarifies that despite the coincidence, it bears no dynamical relationship to the interstellar visitor. Its orbit origin and physical properties are completely distinct. Still, the near-simultaneous discovery of both bodies has amplified public fascination. Across the world, social media threads, scientific forums, and late-night observatories buzz with discussion. What exactly is happening with this comet? Why now? And what might it reveal about the space between the stars? As the days progress, Atlas continues to evolve. Each new image reveals subtle changes in the tails, faint ripples, brightening knots and streams that twist and separate like smoke in slow motion. The anti-tail broadens, fanning outward behind the comet's trajectory. The sunward jet, though narrower, burns with consistent intensity, defying expectations. Observers describe it as if the comet were breathing, expelling light into both directions of the void. Its motion across the constellation Capricorn grows faster with every passing night, and by mid-December, It may even become visible to skilled amateurs using modest telescopes. To witness such an event, an active interstellar comet illuminating our skies is something that occurs perhaps once in a lifetime. Meanwhile, research teams are preparing simulations to compare Atlas motion with theoretical models of gas-driven acceleration. The goal is to test whether the observed changes in velocity can be entirely accounted for by natural outgassing. If not some additional mechanism, perhaps electrostatic forces, magnetic interactions, or unknown thermodynamic effects must be at work. Every parameter from spin rate to surface temperature is under review. The excitement lies not only in solving the puzzle, but in what that solution might teach us about how interstellar bodies survive their eons-long journeys. Each comet is a messenger carrying dust older than our sun, and with it, the story of a distant system that may no longer exist. At this stage of the investigation, Avi Loeb emphasizes restraint. The anomalies, he writes, are fascinating, but not yet proof of anything beyond nature's complexity. Still, he reminds readers that the scientific path begins precisely with such anomalies. Oumuamua's unexplained acceleration in 2017 demonstrated that the universe can surprise us in ways that challenge even the best physical models. With Atlas, we have the chance to observe similar mysteries in real time with far more advanced instruments and coordination. Whether this comet behaves according to physics as we know it or reveals processes yet unseen, the outcome will deepen our understanding of the cosmos and perhaps our place within it. In recent weeks, astronomers have begun to detect subtle fluctuations in the comet's brightness that don't correspond precisely with its rotation period. This has led some to suspect that its nucleus may not be a single solid body, but a cluster of fragments bound loosely together, each venting material at a slightly different rhythm. If true Atlas could be slowly disassembling as it approaches perihelion, releasing gases and dust from multiple active sites. Such a process might explain the continuous formation of the anti-tail and the steady, concentrated jet directed sunward. Even so, the energy required for both phenomena remains unusually high for an object of its size, prompting further investigation. The chemical composition detected so far continues to fascinate. Observations by the Atacama Large Millimeter Array in Chile reveal emissions dominated by carbon monoxide mixed with traces of methane and ammonia elements expected in comets, but in proportions rarely seen. The relative scarcity of water further distinguishes Atlas from typical solar system comets. This suggests that it may have originated in a region where the local star emitted weaker ultraviolet radiation, allowing volatile compounds to freeze without significant loss of hydrogen-bearing ices. If such chemistry is confirmed, Atlas would offer the first tangible sample of an exoplanetary system's frozen material, a direct window into another cosmic nursery. Scientists are particularly eager to determine whether Atlas acceleration after perihelion corresponds precisely to its measured outgassing rate. If the comet's motion exceeds what can be explained by sublimation alone, then an unknown factor is influencing its trajectory. During October, small deviations in its velocity vector were recorded, nothing dramatic, but sufficient to raise eyebrows. The Galileo project's monitoring instruments will soon compare these readings with real-time data collected in December. If discrepancies persist, they could signal unmodeled forces, perhaps asymmetric ejections, or in the boldest hypothesis, an internal mechanism guiding the object's spin or orientation. Still, Avi Loeb and his peers remain cautious. Science advances not through leaps of imagination, but through the patient accumulation of consistent evidence. Loeb reminds his readers that extraordinary claims demand extraordinary data. In the end, Whether 3I Atlas proves to be an ordinary comet behaving in extraordinary ways, or something far rarer, its passage has already achieved something remarkable. It has reminded us of the thrill of discovery, the humility of not knowing, and the beauty of evidence unfolding one image at a time. As telescopes continue to watch its fading glow, scientists will extract meaning from every photon, decoding the silent language of an object born among the stars. The mystery may persist for years, but so will the wonder it ignited. Thank you for joining this exploration. If you find joy in following the universe's unfolding story in evidence-based mysteries that bridge science and imagination, remember to support this channel, share it with fellow explorers, and keep looking upward. Somewhere out there, another traveler like Atlas is already on its way, carrying with it the next chapter of our cosmic story.